your screen. Oh, perfect.
Okay. A good day, ladies and gentlemen. Due to the epidemic control policy in China, Professor Zheng is unable to enter her office room today to complete this talk. She temporarily entrusted me to read out this report for her. My name is Zhu Wei from the Center for Particle Turbulence, Lanzhou University. Today's talk is titled Turbulence Characteristic of Non-Neutral or non-stationary flows in the atmospheric surface layer. Firstly, I would like to introduce the research background of this issue. Non-neutral or non-stationary flows are ubiquitous in atmospheric flows. Here, we take a complete sandstorm event observed by our team as an example. Both wind velocity and temperature data lasting 14 hours demonstrate time-varying change, which is a simple manifestation of non-stationary flow. At the same time, through the analysis of the thermal flux, it can be found that the development of a sandstorm experience unstable, neutral, and stable stratification flows. Lanzhou is a city located in the western region of China, where sandstorms frequently occur in spring season. Sandstorms have caused huge economic losses and ecological damage in northwest China. Sandstorm flow is characterized by two notable features and/or challenges. One is high Reynolds number. High Reynolds number turbulent flow is a core but difficult issue in current turbulence research. Due to the lack of satisfactory theoretical models, both numerical and experimental researches face great challenges. More high Reynolds number experiments are required to deepen the understanding of turbulence dynamics, to improve turbulence models, and to achieve accurate predictions. On the other hand, sandstorm is a typical gas-solid two-phase flows. As Balachandra and Eaton summarized, turbulence and multi-phase flow are two of the most challenging topics in fluid mechanics, and when combined, they pose a formidable challenge, even in the dilute dispersed region. In order to study high Reynolds number particle turbulent flow in the ASL, we set up a field observation facility named the Qingtu Lake Observation Array, QLOA. QLOA is located on the dry lake bed of Qingtu Lake in northwest China, and the surface is flat without vegetation coverage. The surface layer thickness is about 70 to 200 meters, and the frictional Reynolds number is 10 to the power of 5 to 7. Sandstorms frequently occur there, so it is a nature site for observing high Reynolds number water turbulence and particle-laden flows in the ASL. QLOA consists of a main tower of 32 meters and 32 small towers of 5 meters. More than 10 kinds of instruments were installed on the tower to realize multi-element observations. Till now, it has been the only system that can carry out simultaneous multi-point and multi-physics observations concerning sand-laden flows in the ASL. Here shows the observation instruments installed at the site, including ultrasonic anemometers, dust concentration meters, etc. Since 2013, we have carried out long-term synchronous observations on particle-free and particle-laden flows. Till now, we have accumulated more than 7,500 hours of synchronous data, taking more than 4.5 TB. It was commented as unique because this is the field observation side with the largest scale, longest time lasting, and the most complete data, and the highest Reynolds number in the related research field. Based on the observation data, we conducted systematic studies on particle-free and particle-laden flows in the ASL. Here we show the instantaneous column map of flow velocity in particle-free and particle-laden cases, as well as instantaneous PM10 concentration field based on the Taylor's frozen hypothesis, in which the x-axis denotes the streamwise direction, y the spanwise direction, and z the normal direction. It can be clearly identified that a very large scale motion, VLSMS, exists in both the particle-free and particle-laden flow fields, as well as in the PM10 concentration fields. Well, as for the topic, here gives a definition of neutral, stable, and unstable stratification based on the Money-Uphoff parameter, ZL ratio. And flows with ZL ratio less than 0.1 are defined as stable stratification flows, minus 0.1 to 0.1 as near neutral stratification flows, and larger than 0.1 as unstable flows. As a validation, we firstly compare the mean velocity profiles with different stratification conditions, as shown in the left figure. Lines are theoretical solutions for various stratification parameters. Points are measured data at corresponding Z to L values. The right figure shows the components of fluctuating velocity versus stratification parameters. So our measured data are appropriate for investigating non-neutral and non-stationary flows in the ASL. Through linear coherent spectrum analysis, we studied the self-similarity scaling of the VLSMs and the coherence of temperature signals under the unstable conditions. It shows that the flow velocity and the temperature in the unstable flow all follow a self-similarity scaling well in three-dimensional space. However, their scale ratios decrease with increasing thermal flux, indicating the buoyance play a lifting effect, increasing the size of coherent structures in the wall normal and spanwise directions. Under the stable stratification conditions, the linear coherent spectrum show that the turbulent structures no longer satisfy the self-similarity scaling anymore, at least in the observation region. Further, by analyzing the phase spectrum of the flow velocity at different heights, we obtain the variation of inclination angle of turbulent structure with the scale and the stability parameters in the non-neutral stratification flows. The results show that under the unstable conditions, the inclination angle increase with the thermal stability, which is consistent with the existing results. For different scale structures, our data show that the inclination angle decrease with the structure scale. This is a novel result that the inclination angles of turbulence are scale dependent. Next, we analyzed the two-point cross correlation of streamwise velocity fluctuations, RUU, the streamwise spanwise correlation RUV, and the streamwise wall normal correlation RUW under different stability conditions. For the convenience, we classify the data according to ZL ratio ranges as shown in A, B, C, and D. The isocontour maps were averaged to reduce dispersion. From the figure, it can be found that there are positive correlation regions, that is, large-scale coherent structures. Under unstable and stable stratification conditions, thermal buoyancy plays a role in lifting and suppressing large-scale coherent structures, respectively. The streamwise, spanwise correlation RUV exhibits a counter-rotating roll mode between the low and high momentum regions in the spanwise direction. That is, spanwise converging flow close to the wall, while a diverging flow at greater heights. As the thermal buoyancy increase, such roll modes will be larger in diameter with a steeper inclination. Streamwise wall normal correlation RUW shows that low momentum motions are accompanied by the flow away from the wall, with the flow towards the wall occurring some distance away to the span. Such roll modes will be larger and with steeper inclination for unstable cases, while in the stable cases, there are more constrained to the wall. Furthermore, we calculated the correlation coefficients of momentum and thermal flux in the spanwise and wall normal planes. Analyzed their variations with stability parameters. The results show that the normal stress flux in different directions are linearly related and increase with the stability parameters. Correlation between Reynolds stress and thermal flux shows that under near-neutral conditions, shell flow dominates the transport of Reynolds shell stress and streamwise thermal flux, while under unstable stratification conditions, thermal buoyancy dominates the transport. Through the autocorrelation of temperature fluctuations, we quantitatively analyzed the scale variation of the large-scale structure in temperature field. The results show that the streamwise scale of the temperature structure increase with the wall normal height and decrease with the thermal buoyancy. Next, I will introduce the non-stationary characteristics of sandstorm flows and the method we used. This is a complete time series of wind velocity and dust concentration during a sandstorm. It can be seen that one entire sandstorm process includes the rising, steady, and declining stages. In the rising and the declining stages, statistics have obvious time varying factors indicating the flow is a non-stationary flow. Non-stationarity is not only reflected in the time variation of the mean velocity, but also in the fluctuating quantities. Therefore, it is impossible to remove the non-stationary part of the data simply by deleting the mean. In the existing statistical theory of turbulence, the statistical moments of wind velocity, such as mean wind velocity, turbulent intensity, and the two-point correlation, etc., are all time averaged quantities, which are assumed invariant with time. That is time average, and that means time average and ensemble average are equal. While the essence of a non-stationary process is the statistics of which vary with time, not satisfying the time ergodic and autocorrelation ergodic, or saying the statistical convergence. So the time average does not work for non-stationary signals. Furthermore, the Fourier transform is a global transform, and the frequency domain information does not reflect the local characteristics of non-stationary signals. For this reason, some methods have been proposed through adding windows in the time domain, such as short-time Fourier transform, WVD distribution, and wavelet transform, etc. But these methods are all derived based on the Fourier transform. One
lost you. Annika, can you send a chat, see if he's online? If you can hear me, can you turn off your video and see if we can hear you? We can still see your slide. Well, it's probably just stuck, isn't it? Is he online? No, okay. Because we're going to make a joke about a big sandstorm coming through and knocking out the internet. Let's tell us a joke. I did the last one.
Hello.
Hello. Oh, you're back. Good. Very good. We lost you all together there.
Sorry for that.
Can you reshare? Yeah.
Okay,
We dropped off the call.
I lost here or.
No, but there. We were just finishing the right-hand side of that slide, I think.
Okay.
Please, thank you. Go ahead.
Okay. Well, for this reason, some methods have been proposed through adding windows in the time domain, such as short-time Fourier transform, WVD distribution, and wavelet transform, etc. But these methods are all derived based on the Fourier transform. One exception is the Hilbert-1 transform, which jumps out of the framework of the Fourier transform. However, it works only well for time frequency analysis, but cannot present a comprehensive understanding of turbulence statistics and structural features. And many statistical analysis methods have been employed in the study of turbulent structure. For example, two-point correlation, conditional average were used to review the spectral scale and the morphology of turbulent structures. Amplitude modulation coefficients were used to reflect the energy modulation from the VLSMs to small-scale motions, as well as statistical analysis methods, including structure function, linear coherent spectrum, and bispectrum, etc. However, all these time average statistical analysis methods require the stationary condition, which therefore cannot be directly used for the non-stationary signals. Therefore, it is necessary to answer this question. Firstly, how to treat non-stationary signals? Can traditional methods be extrapolated? How turbulent structures evolve during a sandstorm event? Do there exist VLSMs in the rising and declining stages? And what are the differences in the turbulent structure at different stages? The non-stationarity of the sandstorm flows in the rising and declining stages are mainly reflected in two aspects. The first is the long period synoptic scale trend. The typical time for the very large scale motions is about 1/4 to 5 minutes based on the Taylor-Frozen hypothesis, while a common synoptic event called gusty wind have a time period of about 1 to 10 minutes. An overlap in time exists in these two types of structures. So the commonly used high-pass filtering method cannot fill out the synoptic scale trend clearly. The second is the time varying feature of turbulent fluctuations. Through shortening the time length is undoubtedly the most effective method to reduce the time variety. But it doesn't guarantee the statistical convergence, which increase the discreteness of the data, while prolonging the time length will intensify the time varying factor. So traditional filtering methods suffer a dilemma in treating non-stationary signals. The key to non-stationary data processing is to move the trend segments and extract the stationary segments reasonably and effectively. So the first step is detrending. As we know, the VLSMs are slender structure with a span-wise scale of about 0.3 delta, while synoptic structures are global. By arranging multiple measuring points along the span-wise direction, the averaging the wind velocity data at all measuring points, the mean fluctuations reflecting synoptic events can be obtained. Then empirical mode decomposition can be used to extract the trend term from the mean fluctuations. Finally, the trend term can be removed from the original signals, and the trending achieves. Then, for signals after detrending, we proposed an adaptive segmented stationary method based on the idea of adaptive wavelet decomposition. This is a flow chart of the non-stationary data processing. Through this method, a non-stationary signal can be divided into several segments of stationary signals. For the segments that do not satisfy the statistical convergence, we conducted an ensemble average over a larger data set under the same conditions as a compensation for the time average, so as to ensure the reliability of this method. To validate the reliability of this method, we employed a synthetic fluctuating signal consisting of real turbulent fluctuating signals and several artificially aided non-stationary signals. Based on the power spectrum and the pre-multiplied energy spectrum, we found the adaptive segmented stationary method can accurately exhibit the various frequency components contained in the signal and the time varying characteristics. Therefore, it is reliable to deal with non-stationary signals and can be used to process the sandstorm data. Further, we apply the adaptive segmented stationary method to the measured sandstorm data. For the non-stationary segment, we found the longest time series that satisfy the stationary condition. For the stationary segment, the wavelengths corresponding to the pre-multiplied spectrum peak agrees well with the results in the laboratory turbulent boundary layer at low and moderate Reynolds number. Previously reported results indicated that the sand particles and Reynolds number exhibit negligible effects on the wavelengths of the spectrum peak. Therefore, the agreement shown in this figure further confirm the reliability of the analysis methods proposed in this study. The spectral method is a useful and important tool in data analysis. For a signal xt, the case order spectrum can be obtained by a k-1 dimensional Fourier transform of the case order cumulant, which is given as the bottom equation. In particular, when k equals to 2, this equation represents the power spectrum, which reflects the energy distribution at different frequencies. For studies on turbulence, the frequency is usually converted to the length scale by the Taylor's frozen hypothesis. When k equals to 3, we can obtain the bispectrum, which provides a measure of the quadratic interaction, exhibited by the given triad of waves at frequency of f1, f2, and f3 that satisfy the resonance wave matching requirements. That is, f3 equals to f1 plus f2. And a non-zero bispectrum value means that phase coupling will occur between frequency f1, f2, and f3. These figures show the pre-multiplied spectra of the streamwise velocity fluctuations versus the streamwise wave number at different war normal heights in different stages of the sandstorm. It can be seen that the VLSM as exist in both the rising and the steady stages of the sandstorm, while in the declining stage, the VLSMs gradually disappear. Further, the pre-multiplied spectra also demonstrate a reversal phenomenon in sandstorm flows. It indicates that the formation mechanism of the VLSMs during a sandstorm event not only attribute to a bottom-up mechanism, but also to a top-down mechanism. In addition, the turbulent kinetic energy on the right side of the spectrum peak in the rising stage decrease rapidly without a short wave number range, which means that more energy is concentrated in the VLSMS, indicating that VLSMS originally exists in the initial stage of the sandstorm, instead of gradually developing in the later stages.
Let's have a 3-minute warning, please. Could you start to wrap up?
Okay.
Thank you.
This figure shows the energy fraction of the VLSMs in different stages in sandstorm versus war normal heat. It can be found the most significant difference in the 3 stages is that the energy fraction of the VLSMs in the rising stage can reach up to 75%. Well, the left figure shows the evolution of the wavelengths of the spectral peak with time at different heights. There are significant differences at different stages. The scale varies significantly with height in the steady stage, while the scale remain reasonably fixed at different heights in the rising and the declining stages. Through comparison, we found traditional methods significantly overestimated structural scales. As an example, this figure shows the absolute bispectrum of the high frequency band of the streamwise velocity fluctuations in the sandstorm. Obviously, the bispectrum exists multiple peaks at different positions, indicating a strong quadratic phase coupling between the corresponding frequencies. In addition, negative frequencies derived from the bispectrum calculation are nonsense in physics. Thus, only the positive frequency component, that is the first quadrant part, will be shown in the following figures. The top 3 sub-figures present the bispectrum of the streamwise velocity fluctuations in different stages of a sandstorm. The contour maps of the bispectrum in different sandstorm stages are basically the same. Large spectrum values are concentrated in the long frequency region, indicating there is a strong quadratic phase coupling in the long frequency fluctuations during the sandstorm, which causes the large structures to break down into small scale structures. Integrating the bispectrum along one of the frequency direction, we can obtain the integral bispectrum as defined by this equation. The integral bispectrum represents the total nonlinear interaction by all of the other frequency components on a certain frequency. We found the this figure indicates that the peak of the integral bispectrum is significant in the rising stage, and with the evolution of time, the peak gradually weakens in the following steady and declining stages. So the nonlinear energy transfer is the most significant in the rising stage of the sandstorm. Below the dashed line are the VLSMs or LSMs with streamwise length scale larger than 0.3 delta. It means that obvious peaks of the integral bispectrum are mostly concentrated in the long frequency region below the dashed line. The LSM or VLSMs are not only significant energy structure, but also active structures that exhibit significant nonlinear interactions. The integral bispectrum shown in these figures is integrated again in the region below and above the blue dashed line to obtain the total nonlinear interaction occurring in the LSM and VLSMs, the left 3 figures, and small scale motions, the right 3 subfigures respectively. It shows that the integral bispectral value of the LSMs and VLSM is relatively large and is positive during the rising stage of the sandstorm, which means that LSMS or VLSMS gain energy from the nonlinear interaction. In the steady and declining stages, the integral bispectrum values are significantly reduced and vibrates around 0, indicating the energy maintains a balanced budget during the weakened nonlinear interaction process. For small scale motions, the integral bispectral values only vibrate around 0, indicating that the nonlinear interaction process does not change the energy budget of small scale motions during the entire sandstorm process.
Could you wrap up because we're running into our lunchtime? I know you had an interruption, but we would like to have a couple of questions. Thank you.
Okay. This is a brief summary.
Okay, very good. Thank you very much. Yep. Please leave those conclusions up so we can take a look while I see if anyone has any questions in the room. I understand you're presenting on behalf of Professor Zheng, but if there are questions that we can relay back. Anything from the room? Yes, Javier has a question.
Is the mass loading of the sand or the dust, is this large enough so that the potential energy from